Space and Science News with James. In the depths of space, a cosmic puzzle has been slowly revealing itself. Scientists have been peering into the night sky, focusing their attention on some of the most enigmatic objects in the universe, white dwarf stars. These stellar remnants, the dense cores of once vibrant suns, have long captivated astronomers with their extreme properties. But recent observations have unveiled something truly extraordinary. Today, we'll be talking about white dwarf stars and their unexpected behavior, because why not explore the mysteries of the cosmos? A groundbreaking study of over 26,000 of these celestial objects has confirmed a phenomenon that challenges our understanding of stellar physics. It turns out that these ultradense stars don't always behave as we thought they would. What could this mean for our understanding of the universe? How might it change our theories about the life and death of stars? And could it possibly lead us to uncover the elusive nature of dark matter? The implications are staggering, potentially reshaping our cosmic perspective. Let's dive deep into this subject of white dwarf stars and the cutting-edge research that's pushing the boundaries of astrophysics. White dwarf stars are enigmatic remnants of stellar evolution, captivating astronomers with their extreme properties. These dense cores of once vibrant suns have long been subjects of intense study, and now, a groundbreaking survey has unveiled fascinating insights into their behavior. Researchers at Johns Hopkins University have meticulously examined over 26,000 white dwarfs, confirming a long-predicted phenomenon: hotter white dwarfs are slightly puffier than their cooler counterparts, even when they possess the same mass. This discovery marks a significant step forward in our understanding of these stellar corpses. White dwarfs are incredibly dense, with a teaspoon of their material weighing upwards of a ton. Their extreme density results in a gravitational pull hundreds of times stronger than Earth's, creating an environment where the laws of physics are pushed to their limits. These stars spend most of their existence cooling down, with surface temperatures ranging from a scorching 40,000 K to a relatively cool 4,000 K. The confirmation of this temperature-size relationship brings scientists one step closer to using white dwarfs as natural laboratories for probing the effects of extreme gravity and hunting for exotic dark matter particles. This research not only validates existing theories but also opens new avenues for exploring the mysteries of the cosmos and the fundamental laws that White dwarfs are the fascinating remnants of stars that have completed their main evolutionary phases. These stellar corpses represent the final stage for the majority of stars in our universe, including those similar to our Sun. White dwarfs form when stars with initial masses up to about 3 or 4 times that of the Sun exhaust their nuclear fuel and shed their outer layers. The structure of a white dwarf is unique and layered. At its core, a typical white dwarf is composed primarily of carbon and oxygen, the waste products of previous nuclear fusion reactions. Surrounding this dense core is a thin envelope of helium, and in most cases, an even thinner layer of hydrogen. This stratified structure is a result of the immense gravitational forces at play, which separate elements based on their atomic weight. The extreme density of white dwarfs is one of their most remarkable features. With a mass comparable to our Sun compressed into a volume similar to that of Earth, the density of these objects is almost beyond comprehension. This compression results in a gravitational pull hundreds of times stronger than Earth's, creating an environment where the laws of physics are tested to their limits. In white dwarfs, the pressure of gravity is counterbalanced not by ongoing nuclear fusion, but by electron degeneracy pressure. This quantum mechanical phenomenon prevents further collapse, allowing these stars to exist in a stable state for billions of years. As they have exhausted their nuclear fuel, white dwarfs slowly cool over time, radiating away their residual thermal energy. The research team employed an ingenious method to study white dwarfs, focusing on the gravitational redshift effect. This phenomenon, a cornerstone of Einstein's theory of general relativity, occurs when light escapes from massive objects. As light travels away from the intense gravitational field of a white dwarf, it loses energy, causing its wavelength to stretch and shift towards the red end of the spectrum. This redshift effect serves as a powerful tool for scientists to probe the extreme gravity surrounding white dwarfs. By measuring the extent of this redshift, researchers can gain valuable insights into the mass-to-radius ratio of these dense stellar remnants. The more massive and compact the white dwarf, the stronger the gravitational redshift observed. The team's approach involved analyzing data from thousands of white dwarfs, allowing them to average out other effects like Doppler shifts caused by stellar motion. This statistical method enabled them to isolate and measure the gravitational redshift with unprecedented precision, providing a robust test of general relativity in these extreme environments. The confirmation of this effect not only validates Einstein's predictions but also offers a unique window into the structure and composition of white dwarfs. By combining gravitational redshift measurements with other observational data, astronomers can refine models of white dwarf interiors and evolution, potentially shedding light on the final stages of stellar life cycles. The relationship between mass and size in white dwarfs is counterintuitive and fascinating. Unlike main sequence stars, where more massive stars are larger, white dwarfs exhibit an inverse relationship. The more massive they are, the smaller their radius becomes. This peculiar behavior stems from the unique physics governing white dwarfs. As these stellar remnants lack the nuclear fusion that supports normal stars, they are held up against gravity by electron degeneracy pressure, a quantum mechanical phenomenon. This pressure, which does not depend on temperature to first order, increases with density. The mass-radius relationship for white dwarfs follows a pattern where the radius r is proportional to mass m, cube root, minus 1/3. This means that as the mass increases, the radius decreases. The increased weight of a more massive white dwarf requires a stronger pressure gradient to support it, resulting in a smaller, denser star. Recent research has refined our understanding of this relationship. Scientists have found that temperature does play a role, especially for white dwarfs above 10 to the power of 7 K. Additionally, the mass radius curve shows a maximum radius occurring between 0 and 1 solar mass, with the curve arcing downward for both lower and higher masses. Interestingly, white dwarfs cluster around 0.6 solar masses, with a narrow mass distribution. The most massive white dwarfs approach the Chandrasekhar limit of about 1.4 solar masses, beyond which electron degeneracy pressure can no longer support the star against collapse. The study of white dwarfs has been greatly enhanced by the collaborative efforts of two major astronomical projects, the Sloan Digital Sky Survey, SDSS, and the European Space Agency's Gaia mission. These initiatives have revolutionized our understanding of the cosmos by providing unprecedented amounts of data on celestial objects. The Sloan Digital Sky Survey, which began in 2000, uses a dedicated 2.5-meter wide-angle optical telescope at Apache Point Observatory in New Mexico. This telescope, with its 3 degrees distortion-free field of view, has been instrumental in creating detailed three-dimensional maps of the universe. The SDSS has produced deep multicolor images of 1/3 of the sky and spectra for more than 3 million astronomical objects. In its latest phase, SDSS-4, the survey has expanded to include observations from the southern hemisphere, using the Irénée Dupont telescope at Las Campanas Observatory in northern Chile. This expansion allows for a more comprehensive view of the sky, enabling researchers to study celestial objects across both hemispheres. The Gaia mission, launched by the European Space Agency, complements the SDSS data with its own stellar surveyor. Gaia has been scanning the sky since 2013, providing high-precision measurements of positions, distance indicators, and proper motions for more than 1 billion stars in our Milky Way galaxy. The combination of these two projects has created a powerful synergy in astronomical research. While SDSS provides detailed spectroscopic data, Gaia offers precise astrometric measurements. Together, they allow astronomers to study the structure, composition, and evolution of stars, including white dwarfs, with unprecedented accuracy and detail. The recent findings on white dwarf behavior have opened new avenues for exploring stellar evolution. The research provides valuable insights into the final stages of a star's life and the processes that determine its ultimate fate. One of the key areas of interest is the relationship between a star's initial mass and the mass of the white dwarf it eventually becomes. This initial to final mass relation is crucial for understanding how stars evolve and end their lives. The study has revealed that this relationship is more complex than previously thought, with low-mass progenitor stars capable of producing a wide range of white dwarf masses. The next frontier in this field, as suggested by Professor Nadia Zakamska, involves detecting subtle differences in the chemical composition of white dwarf cores with varying masses. This could provide crucial information about the internal processes that occur during a star's lifetime and its final stages. Understanding the maximum mass a star can have to form a white dwarf is another critical aspect of this research. Current estimates suggest that stars with initial masses up to about 8 solar masses can become white dwarfs. However, the exact limit and the factors influencing it are still subjects of ongoing research. These findings also have implications for our understanding of more exotic stellar remnants like neutron stars and black holes. By refining our knowledge of white dwarf formation, we can better predict which stars will collapse into these denser objects. White dwarfs have emerged as promising candidates in the ongoing search for dark matter. These dense stellar remnants offer unique opportunities to probe the nature of this elusive substance that makes up approximately 85% of the matter in the universe. Recent research suggests that white dwarfs could serve as natural detectors for dark matter particles. Their extreme density and strong gravitational fields make them ideal environments for capturing and concentrating dark matter. Scientists propose that if dark matter particles are present within white dwarfs, they could potentially annihilate, producing excess heat and gamma rays. Different dark matter models predict varying effects on white dwarf structures. For instance, some theories suggest that dark matter could create interference patterns in galaxies. If two white dwarfs are located within the same dark matter interference patch, their structures might be altered in identical ways, providing a potential observational signature. The study of white dwarfs may also help distinguish between competing dark matter theories. Simulations have shown that different dark matter models, such as cold, warm, and fuzzy dark matter, would have produced distinct patterns in the formation of early galaxies. By examining the properties of white dwarfs, astronomers hope to find clues that could support or rule out certain dark matter candidates. Furthermore, white dwarfs are particularly sensitive to ultra-heavy dark matter particles, which are challenging to detect through traditional methods. This makes them valuable tools in exploring a wider range of dark matter mass scales. As observational techniques improve, astronomers anticipate that studying white dwarfs could reveal subtle effects of dark matter interactions, potentially leading to groundbreaking discoveries in this field. Dark matter remains one of the most intriguing mysteries in modern astrophysics. This invisible form of matter does not emit light or energy that telescopes can detect, yet its presence is felt through its gravitational effects on stars, galaxies, and other cosmic objects. Scientists infer its existence from the way galaxies rotate and the distribution of mass within galaxy clusters, which cannot be explained by visible matter alone. The influence of dark matter on celestial bodies is similar to how the Sun affects Earth's orbit. For instance, the rotation curves of galaxies remain flat at their edges, indicating that stars in these regions are moving faster than expected, suggesting the presence of unseen mass. This phenomenon is a hallmark of dark matter's gravitational pull. Dark matter is thought to make up a significant portion of the universe's mass-energy content, playing a crucial role in the formation and evolution of galaxies. Its presence helps explain why galaxies cluster together and why the universe's large-scale structure is as it is. Despite its importance, dark matter remains elusive. Scientists have proposed various candidates, including weakly interacting massive particles, WIMPs, and axions, but none have been definitively detected. Researchers continue to employ innovative methods to uncover dark matter, from direct detection experiments to indirect detection through astrophysical observations. As the search for dark matter continues, scientists hope to unravel its mysteries and understand its role in shaping the cosmos. Understanding simpler astrophysical objects like white dwarf stars plays a crucial role in unraveling the mysteries of dark matter and fundamental physics. White dwarfs, being among the most abundant stellar remnants, offer unique opportunities to probe dark matter interactions in ways that complement terrestrial searches. These ultradense stars serve as natural laboratories for testing extreme physics. Their incredible density, with a mass comparable to our Sun compressed into a volume similar to Earth's, creates an environment where gravitational and quantum effects interplay in fascinating ways. This makes white dwarfs ideal for studying fundamental physical processes under conditions impossible to replicate on Earth. Researchers use white dwarfs to test various aspects of physics, including gravitational physics, quantum mechanics, nuclear physics, particle physics. By thoroughly comprehending the physics of these well-characterized stars, scientists can potentially distinguish between known phenomena and novel effects that might point to new fundamental physics or exotic particles. For instance, the study of white dwarf cooling rates and internal structures could reveal subtle effects caused by dark matter interactions or other unknown particles. The recent survey of over 26,000 white dwarfs has confirmed a long-predicted phenomenon: hotter white dwarfs are slightly larger than cooler ones of the same mass. This finding not only validates existing theories but also provides a foundation for more precise measurements that could uncover unexpected deviations from standard models. As our understanding of white dwarf physics improves, these stars may help constrain dark matter models or even lead to the detection of dark matter particles. Some researchers suggest that dark matter could be captured and annihilate within white dwarfs, producing observable effects such as excess heat or gamma rays. Astronomical research increasingly relies on large-scale collaborations involving multiple institutions and funding sources. These partnerships enable scientists to tackle complex questions about the universe by combining diverse expertise and resources. Major collaborative efforts in astronomy include the Vera C. Rubin Observatory, which will conduct the Legacy Survey of Space and Time, LSST. This project involves over 30 institutions worldwide and aims to address fundamental questions about our universe. The LIGO Scientific Collaboration, which has made groundbreaking discoveries in gravitational wave astronomy. This collaboration includes researchers from numerous universities and research centers globally. The LISA Consortium, working on a space-based gravitational wave detector scheduled for launch in the coming decade. The Giant Magellan Telescope Project, which involves multiple founding partners, including Northwestern University, to build an enormous ground-based telescope in Chile's Atacama Desert. The NSF Simons AI Institute for the Sky, SKAI, led by Northwestern University, which combines astrophysics and artificial intelligence to analyze data from revolutionary sky surveys. These collaborations are supported by various funding sources, including the National Science Foundation, NSF, which provides grants through programs like the Astronomy and Astrophysics Research Grants, AAG. The NSF also supports national astronomy centers and international facilities like the Gemini Observatory and ALMA. Such collaborative efforts enable astronomers to pool resources, share data, and work together on complex projects that would be impossible for individual researchers or institutions to undertake alone. As we reflect on the fascinating world of white dwarf stars, it's clear that these celestial bodies hold more than just a passing interest for astronomers. They are natural laboratories where extreme gravity and quantum mechanics converge, offering scientists a unique opportunity to test fundamental theories of physics. The recent study of over 26,000 white dwarfs has not only confirmed a long-predicted effect but also opened new avenues for exploring the mysteries of dark matter. The implications of this research are profound. By understanding the intricate details of white dwarf behavior, scientists may uncover clues about the elusive nature of dark matter, which remains one of the biggest enigmas in modern astrophysics. The precision and scale of this study demonstrate the power of collaborative research and advanced astronomical tools like the Sloan Digital Sky Survey and the Gaia mission. As we continue to explore the cosmos, discoveries like these remind us of the awe-inspiring complexity and beauty of the universe. They inspire us to delve deeper, to question more, and to seek answers to the mysteries that surround us. Thank you for joining us on this exploration of white dwarf stars. If you found this video enlightening, please consider subscribing to our channel for more insightful content about the wonders of science and the universe. Your support helps us continue to share fascinating stories and discoveries with you. Until next time, keep exploring and stay curious. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.